Welcome, this is Coach Silver, and this is a podcast on electric current. We're going to start out talking about voltage. This is no doubt something you've heard and probably used before in sentences talking about voltage. Voltage is also known as electric potential. Anytime there is a difference in voltage, or electric potential, current will flow, charge will flow. So anytime you have a difference in voltage from one spot to another, and there's a conducting path between the two spots, you will have flow of charge. The flow of charge will continue until the difference in potential, the potential difference, is zero, until there's a common voltage that's reached. And in order to sustain a flow of charge, you have to have something that maintains a higher voltage in one area than another. This is what we're going to be exploring in this podcast. It might help to think of electricity flow as water flows. If you have an area of higher water pressure and an area of lower water pressure, water will flow until the pressure equalizes. If you want to keep that flow going, you have to have a pump. In the case of electric current, that pressure is what we call voltage, or the electric potential. And the pump would be a battery that would keep the difference in pressure from one area to another. Electric current is the actual flow of charge. Voltage is the electric pressure, and current is the actual flow. And it's measured in a unit called amperes. Now, an ampere is the way we measure current. It's the unit of current flow. We write that as a A. And what an ampere is equal to 1 coulomb per second. Now, for what we're doing, the most important thing about this is that you remember that current flow is measured in amps. The electric pressure is measured in volts. In order to keep current flowing, you have to have a potential difference from one part of a circuit to another. A voltage source is what keeps that difference in voltage from one area to another. A battery and a generator are examples of voltage sources. A generator converts mechanical energy into electrical energy. A battery converts chemical energy into electrical energy. And it keeps a potential difference across a circuit so current can flow. If you get rid of that potential difference, you no longer have flow. It is very important to understand the difference between current and voltage. Voltage is the electric push or pressure. Voltage is across a circuit. It's established across a circuit. Current is flow through a circuit. Charge flowing through, that equals current. And that's measured in amps or amperes. Voltage is electric pressure. Current is electric flow. Electric resistance is what it sounds like. It is a measure of the resistance of the electrons to flow in a circuit. We call electric resistance. Just like with this bucket here with the holes at the bottom, a wire that is thicker and shorter has less resistance than a skinny long wire that's going to have more resistance. The greater the resistance, the less the current flows. The lower the resistance, the easier the current flows. So high resistance, low conductivity, low resistance, high conductivity. Here we are back at our water pump example. You can see the pump is the analogy for the battery. The valve is the analogy for the switch. The wavy water line is the analogy for electrical resistance. And the electrical resistance, it could be the light bulb, it could be the radio, it's whatever you're powering up in that circuit. Again, I just mentioned this, but thick wires have less resistance than thin, and longer wires have more resistance than short wires. This all brings us to Ohm's law, which is the relationship between current, voltage, and resistance. It is essential for understanding how all these play out in a circuit, and it states that the voltage in a circuit is directly proportional to the current and the resistance is inversely proportional. So the current is equal to the voltage over the resistance. A lot of times the letter I is used to represent current, V for voltage, R for resistance. You could use the triangle method to help solve Ohm's law's problems. Voltage, current, multiplied by resistance. If you want to know, the resistance of something, you cover up the R and it's voltage divided by amps. If you want to know the amps, it's voltage divided by resistance. If you want to know the voltage, it's current times resistance. That's one way to look at it. If you're not comfortable with that method, don't use it. But you need to understand that Ohm's law is the relationship between current, voltage, and resistance, and it is stated right here. Pause here, take a minute and read this statement and make sure you understand it, that it makes sense, and if it doesn't, then come to class and we shall talk about it. This just gives some resistance values of different wires. Typically, if you have wires just connecting things, the resistance needs to be very, very low. If you have something that actually does some type of work, like a light bulb or a toaster or an iron, they're going to have a certain resistance value. The lower the resistance, the greater the flow of electrons. So something like the iron and the toaster, which has a resistance of 15 to 20 ohms, is going to have a much higher current flow for the same voltage than something that is 100 ohms, because you've got your current equals volts over resistance. You have 120 volts coming out of your wall. If the resistance is greater, the current's going to be lower. If the resistance is lower, the current's going to be greater. This slide just shows a picture of what typical resistors look like on a circuit board. And this slide shows a typical, average, everyday conversation that people might have about electricity. These next couple slides just show some basic information. FYI about resistance, why when you're wet it's more dangerous to be on electrical equipment because your overall resistance drops. Some interesting reading. And again, take all the time you need here. Now, it is the current that is what is dangerous, what can kill you when you get shocked, not the voltage. A lot of you touched the Van der Graaf we had in class. That Van der Graaf is building up a voltage of hundreds of thousands of volts, but the current is very small. It's current that kills, not voltage. And just another of the many slides in this one that are for your reading pleasure. Pause it, read it. You might have seen birds perched on wires before. The reason, and if you've ever wondered why they don't get shocked, the reason is there is no difference in potential. If they're just touching the wire, that's like you touching the Van der Graaf and sitting on the wooden stool. You're building up a charge just like the wire, but there's nowhere for it to go. There's no difference in potential. If you reach over and grab another power line or touch the ground, then you're going to have some problems. Now, you probably have also seen plugs where they have that third prong on them. That's called the ground. And what that is, it's an extra wire that's connected to the surface of the appliance and to other ground wires, which ultimately lead to literally the ground. In a car, it leads back to the negative side of the battery. This is a level of protection. If something shorts out and causes current to flow over the part of a device and you're touching it, instead of the current flowing through you, it will be directed through this ground, which offers it a lower resistance path to ground than your body, and it's a layer of protection. That's what the ground wire does. It diverts any current that's flowing in the wrong place back to a ground instead of through a person. Alright, now it's time for some AC/DC. Not the band though, the electric current. There's two types of current. There's alternating current, direct current. Direct current is more of what you think about when you think about current. It's an electron flowing from point A to point B. And direct current is what is produced by batteries. It means that the electrons are moving from one point in a certain direction to another point. And if you were to graph that of current flow over time, it looks like this. Alternating current, on the other hand, fluctuates back and forth. It's a vibration of electrons. They move in and out, in and out, in and out. A graph of that makes a sine wave. This is the current that comes out of your wall that's produced by generators. It's transferred from the power lines to your house. There are two different types, different ways that electricity can transfer energy. Something very interesting about AC current is, for example, the outlets in your house. You pay for energy coming out of those outlets, but you do not get a single electron out of those outlets. The electrons are already in all the wiring of your house. And it's not like in the case of DC current where an electron comes in, pushes another one out, makes its way through. With alternating current, you're paying for the energy, and the electrons that are already in your wires are being pulled and tugged back, and pulled and tugged back at a certain frequency. So alternating current, you're not actually gaining any electrons. It's energy that's transferred. The electrons are moving out and back, out and back, out and back, as opposed to direct current, which is where an electron does flow through a circuit. But either way, the whole point of electricity is to transfer energy. Now, many devices that you plug in can also be run on batteries. In that case, there needs to be some method of switching the AC current to a DC current. And that's what a converter does. Part of that uses a diode. A diode is a one-way valve for electricity. It lets current flow in one direction but blocks it in the other. So it might let electricity flow in the direction of this arrow so that it can flow one way, but if it tries to flow back in the other direction, it gets blocked. A diode is a one-way valve, a check valve for electric current. That's only half of it though. A capacitor, if you have the one-way valve, the diode, what that does is it takes a AC signal that's alternating back and forth and only gives you the part in one direction. So then you have these gaps. A capacitor is needed to store the charge and smooth out those gaps. Here's a graphical representation of how they work together. The diode would cause it to go from A to B and only allow current flow in one direction. The capacitor kind of fills in the gaps by smoothing out the signal and creating a smooth DC voltage signal. So that is how devices that operate on DC voltage can still be plugged into an AC outlet through a converter. Now, something that you might not have thought about is, how fast is this current actually moving? In the case of DC current, you have electrons. They move pretty fast. They can move at almost the speed of light. Are they moving that fast through the wires? Well, the answer is no. The energy does move at the speed of light. As soon as an electron is applied to one side, energy is transferred to the other. If you think of it like that, they do move pretty fast. Now, on the other hand, electrons are moving around and vibrating very fast inside the wires, but they have no net movement unless there's a voltage. If the voltage is applied, they do have a net movement called drift speed, but it's extremely slow, 0.01 centimeters per second in your average car. So the energy is immediately applied whenever you need it, when you turn the key, but a single electron has a very slow overall movement through the wires. This is an exaggerated view of the average speed, net speed of an electron. While it's going through random motion, if there's a voltage, it's also moving in a certain direction. And again, this is in DC current. Like was previously stated, in an AC current, the electrons don't make any net progress in one direction because they're being pushed and pulled. And it's the pattern, the oscillations of them, that transfer the energy. What you pay for from the power company is energy, not electrons. In the case of an incandescent light bulb that produces light and heat because of electron movement through a filament, because each end of the filament is ultimately connected to a power supply, but it's not gaining or losing electrons. The electrons are being moved back and forth inside that wire that is creating the light, and in the case of an incandescent bulb, a lot of heat as well. So power companies sell you energy, not electrons. Just a couple more things here. Electric power is the rate at which energy is converted into another form. It's the rate at which something is done with this electrical energy that you're getting. Electric power is measured in watts, just like the power we've already learned about, work over time. It's equal to the product of current multiplied by voltage. 1 watt equals 1 amp times 1 volt. If you look down at Mr. Mouse in the bottom right hand corner, he's telling you that 1 watt equals 1 joule over 1 coulomb, which is the definition of a volt, how many joules per coulomb, how much power you have per electron, multiplied by how many coulombs go by in a second, which is a measure of electric flow, which is current. And that equals 1 joule for every second by canceling out the columns. Look at the math on this. This tells you that 1 watt equals 1 amp times 1 volt. Electric power is how much joules you're using every second. Ta-da! And to wrap things up with a real-life example, the power and voltage on the light bulb, if it's a 60-watt light bulb, ran on a typical 120-volt outlet in your house, the amperage it would use would be 0.5 amps. This is one way you can use the power. You could also work backwards and find how much watts you're using. You can also then use this to figure out how much it's costing you to run that per unit of time if you know how much the electric company charges you for the rate that you use the energy. Well, that wraps up this. Until next time, may the mass times acceleration be with you.